In this video, I'll be talking about the electric field due to an infinite set of charges. Let us consider we have an infinite set of charge. This infinite set of charge, and we assume this is a positive charge plane. And we are interested in finding out the electric field at a point P, which is at a distance r from the plane. In order to find out the electric field at this point, we're going to use the Gauss Law. And what does the Gauss Law tell you? First, we're going to create or assume an imaginary Gaussian surface. Again, you can choose any sort of the Gaussian surface, but just to make life easier or to make the integration easier, we're going to choose a Gaussian surface in the form of cylinder. So we have assumed this Gaussian surface, this cylinder, as a imaginary Gaussian surface. All right, this is the Gaussian surface. And remember, this is an imaginary Gaussian surface. Now just take a look at what is the flux passing through this Gaussian surface. The first thing, if you look at this cross-sectional area, the electric field is passing parallel to this cross-section area. All right, and the area vector at this point over this cross-sectional area, the area vector and the electric field vector are parallel. The same thing happens here. The electric field and the area vector are parallel. But now if you look at, let's say, over this side here, at this point the electric field is away from the charge plane, and this is the area vector, which are mutually perpendicular. What does that mean? That means there is no electric flux coming out of this region or this region. The flux due to this charge plane is only coming out of this cross-sectional area. That is, the flux is passing only through this area or through this area. There is no flux coming out of this side or this side. Okay, as this is a charge plane, we assume the sigma is the surface charge density of this charge plane. So now let's find out what is the total charge enclosed by this Gaussian surface. Okay, so the total charge enclosed by this, so only this portion has the charge enclosed, and we know that the cross-sectional area of this one is A. We have assumed the cross-sectional area of the cylinder is A. So the total charge enclosed is simply equal to sigma times A, because sigma is the surface charge density. That means the charge per unit area. So if you multiply by the area, then that gives you the total charge enclosed. Now we're going to use the Gauss law. The Gauss law tells you this is the Gauss law. And this term, this integration term, the integral term tells you the total flux passing through the Gaussian surface. And this is the charge enclosed by the Gaussian surface, and this is the permittivity of the medium. Now, the flux is only coming out of this area and this area. There is no flux coming out of this area, as I mentioned earlier, because at this point the electric field and the area vector are mutually perpendicular. This is the area vector and this is the electric field, which are mutually perpendicular. So the angle between them is 90 degree, and cosine 90 degree is 0. Okay, and also you see this is E vector dot dA vector. That means it's a dot product. The dot product is defined as E times dA times cosine theta. All right. So the flux is it coming out of this area. If you look at any point on this circular cross section, the electric field is constant because we have assumed this to be infinitely long charge plane. Infinitely long charge plane. So the electric field at any point on this cross section area is constant. That's the reason we have assumed it to be infinitely long. Now let's say if this is not infinitely long, then there would be some fringe field coming out of this charge plane, and this would contribute some electric field at this point. And this is the reason we have assumed this charge plane to be infinitely long. So the total flux is now the electric field times this area and the electric field times this area, because the flux is coming out of these two regions. And we have exactly written that EA plus E times A. Here A is the cross-sectional area of this circle here. And now the total charge encloses sigma times A. So what if you solve for E, you get is sigma times epsilon naught. So it is not dependent on the area, or it does not depend upon this distance, which means the electric field due to a charged plane is constant. It doesn't matter where you measure, at this point or this point or this point or a long distance. If it is a charged infinitely long charged plane, the electric field at any point is constant. So that's what it means. So electric field is constant due to a charged plane. It does not depend on the distance. It only depends upon the surface charge density and the medium in which the point is. So this is it for the electric field due to an infinite set of charge.